name is Maria. My background is primarily in sociological research, area in which I'm currently pursuing a PhD in at the University of Essex in England, and in which I worked for 3 years in private sector. Today I'll give you a small glimpse into the research project I'm currently working on. So this project is on the mediating role of education on the transitions of young people in different socio-economic positions into the labor market. Now, the problem I had in trying to capture the key aspects of these socio-economic positions was that I ended up with dimensionality of data too high for my sample size. This is because I had to factor in individual but also parental backgrounds and do so as a dynamic rather than a static feature. So in order to do my analysis, I decided to use cluster analysis as a data reduction technique. And that's the part of the project that I'll be presenting today. The project is way bigger than this little part. So just to quickly give you an idea of the sample I was using, it was from a longitudinal study called Next Steps, which followed young people born in England between 1989 and 1990, between the ages of 14 and 21, that was yearly, with a one-off follow-up at the age of 25. The advantage of this survey was that both the young people and their parents were interviewed face-to-face, so hopefully providing more accurate data instead of relying on recall of young people about their, parental backgrounds and, what jobs their parents had and so on. I analyzed young men and women separately, but the methods I used for this section of analysis were identical. So today I'll just present a sample of women, which after cleaning was just over 4,000. So much smaller than you guys had, but still workable. It's tough with longitudinal data. So now researching youth transitions, for me it was fairly obvious that I needed to take a dynamic approach, but I wanted to illustrate this point more visually. So to give you an idea, I'll show you one of the clustering variables that I used, which was the highest socioeconomic class of a household recorded in wave 1. That I plotted using the function longCatPlot from package longcat EDA. I also have a list of all the packages on the final slide in case you want to write any of them down. So this variable was recorded for the first 4 waves of data collection. Each of the colors corresponds to a major socioeconomic group in reverse order. So it goes from 1 being the lowest class and 8 being the highest. The data is also sorted by the initial socioeconomic position in wave 1. And if you see any white lines, those are missing values. So as you can see, there's a fair bit of movement, to both higher but also lower socioeconomic classes over time. And this is a very important point because each of these time points represent a different stage in a young person's life. So, it could be a point where young people are deciding what subjects to study and to graduate in, then whether to enroll into university and which university to go to, whether to stay closer to home and save money on living costs, or whether they can freely choose whichever university they want. So all these decisions are very much dependent on the parental, socioeconomic and financial backgrounds. So if these change, then the trajectories of young people themselves can change. So I think this is a strong point to make and to support the need to include repeated observations rather than, just sort of arbitrarily choose one point in time. So now that I established this is what I needed to do, needed to include repeated observations of individual and parental backgrounds, I had one more problem to take care of, and that was missing values. There are various sources of missing values in my data set. There was item missing, or non-response to a particular question, unit missing, non-participation, or attrition, so dropping out of study altogether. I included a sample of people that took part in the follow-up stage at the age of 25, because that's where all my outcome variables were recorded in. And this was a subset of anyone who participated in wave 1, so at the age of 14. So this sample included people who took part in wave 1, but then could have dropped out over the course of the study, but then they were picked up again at the age of 25. So looking at the patterns of missingness that I plotted using aggr function from the package VIM, and looking at the frequencies of the missing values, you can see that some of them are pretty high, especially income, which is really not that uncommon in social surveys. But the good sign was that it wasn't all due to unit non-response. It was more about, people refusing to answer certain questions. So you can see a selection of the patterns in the graph on the right, but you can, that came out way smaller. Nope. Sorry. But you can also see the full list of participants using the missmap function in package Amelia. So each line represents a single participant, and the black lines represent missing values. So looking at these frequencies and patterns, it sort of gave me hope that, using the right algorithm, I could impute these missing values. And also the reason I chose to impute in the first place was because certain clustering algorithms don't handle missing values, but also I wanted to make sure that the clustering is done on, people's characteristics rather than their patterns of missingness. So for this particular analysis, I chose to impute using random forests, mainly because it's a non-parametric method that requires, minimal assumptions on the side of the researcher about the variables, and it handles categorical and continuous variables. For more precise imputation, I also included educational variables in the imputation model, even though they were not used to create the clusters, but they were used in further analysis. I did not, however, include the outcome variables in the imputation model, and that's just because I like to take a more conservative approach, rather, encountering false negative than a false positive. Again, just to give you a little illustration of how the imputation went, which I did using missForest in a package with the same name. I have the same variable that I talked about earlier. It's the socio-economic class of the family in wave 1. And in this graph, the purple area represents the overlap between imputed and observed values. The red caps are suggest too many imputed values, and the blue caps suggest not enough imputed values, so too many observed values in those frequencies. We don't know the real distribution of this variable is, but if we sort of assume that it mirrors the observed one, I think we can say that the imputation went pretty well. So now that everything was ready, all my data was ready, I could finally move on to clustering. I won't go into too much detail about each of the clustering variables, but altogether there were 8 unique variables and all their repeated observations, so totaling 24 clustering variables. And they were a mixture of continuous, ordinal, nominal, and binary. So regarding the clustering process, I decided to use Gower's formula to calculate the distances. I did this in R using the DAISY function in package cluster. I mainly chose Gower's distance using DAISY because it calculates pairwise dissimilarities between variables, so it handles both continuous and categorical variables in a data set. So after calculating this dissimilarity matrix, we can, for instance, look at the most similar and dissimilar observations in our data set, which are these pairs. But more importantly, we can use this matrix as an input into the partitioning around medoids algorithm to create our clusters. So the PAM function is from the same package cluster. Now I wanted to have a number of clusters that was big enough to capture the differences in young people's socioeconomic positions, but not too big so that these differences are marginal and that the sample sizes within clusters are too small, so defeating the whole point of data reduction in the first place. So in order to find the right number of clusters, I looked at the silhouette width, which is a metric that takes into account the distance between an observation and other observations in the same cluster, and also the distance from the closest neighboring cluster. So you're looking for sort of the highest value of the silhouette width, and here it would seem that anywhere between 4 and 6 would be great. As I mentioned, I did the same for a sample of men, and I wanted to have the same number of clusters for both these genders because that was optimal for my following analysis. So in the end, I chose 5 as the right number. And so finally, putting my dissimilarity matrix into the partitioning around medoids algorithm with k set to 5, I got a very nice summary of all the 5 clusters. And so you get a summary of the frequency of every of the clustering variables for each of the clusters. So this is cluster number 1, number 2, and so on. So I use these summaries to describe my clusters, and more importantly to sort of order them from the lowest socioeconomic class or position to the highest socioeconomic position of young people, to then add this variable into my analysis. I also wanted to visualize this cluster membership, but because I used 24 clustering variables, it would be, yes, it would be pretty much impossible to just go on and try and plot this and make sure that, humans can read that. So instead, I came across this really handy function called rtsne in a package with the same name, which basically converts it into a two-dimensional graph. But also it takes care of the overcrowding problem, which if you have too many variables that have sort of equally small distances between them, they can, get clustered and it can get less clear. But this function takes care of it. So I used this function, and then I used a simple ggplot to actually visualize it, and I got this beautiful thing. You can see that, you can use this function and illustrate sort of how well or how badly the clustering went. And in my case, I think it went pretty well. There's some overlap, especially cluster number 3, I would say, is spilling over a little bit. But, trying to cluster young people based on what I would say a handful of variables, I think this one pretty well. So next step was to take these socioeconomic positions or cluster memberships and look at how returns to education differ for young people in each of these different clusters. And unfortunately, it's out of the scope for this particular presentation, but I think it's really interesting to mention that I found evidence that there is still inequality, not just to access to education, but actually returns of the same forms of education for these different groups of young people in different socioeconomic positions, which of course I think is a very important thing to mention, especially in the context of really expensive university education in England and massive push for it in the current context. So before I run out of time, just to summarize, so I showed you a tiny bit of what I've been working on, mainly around using cluster analysis as a data reduction technique for both continuous and categorical variables, but also some of the preparation that went into it, such as visualizing sort of the dynamic nature of categorical variables, but also exploration and treatment of missing values. Thank you. Yes?
I tried using cluster analysis mainly in business. The problem I always run into, I try to construct a narrative around the clusters, and I constantly question my own narrative because, like, in your case, cluster number 3 was kind of all over the place. And then, I'm saying to myself, oh, well, if I stick to those clusters, how do I defend them? How do I defend them when somebody comes to me and questions? Do I really believe in those clusters? So I'm just wondering, how did you deal with this problem?
Okay, so just to repeat it, the question, how do I defend my clusters? Well, I think, looking at the visuals, yes, it is spilling over, and of course, you can't say that they're absolutely distinct and the boundaries are absolutely clear. But looking at the summaries, it was a bit more obvious. So I constructed sort of brief summary of every cluster in relation to the clustering variables, but then I also looked at the distributions within each cluster on, the educational backgrounds that I was using in further analysis. And I think when you're trying to defend your own cluster, it's always going to be different. So I would say, unfortunately, in my case, I was able to group people into different socioeconomic positions. I say unfortunately because it, points to inequality, which ideally wouldn't be in the world. But if it mixes too much, then I don't think you can necessarily defend it. But is that a bad thing? Maybe you cannot cluster people. Maybe it's not the right tool that you should be using in your case. I think we need to give a chance to one more question. I think that's it. Yeah.
Okay. So how do you define someone's socio-economic status?
How do I define socioeconomic status? What?
So like how much income they earn, or what's the highest degree they have earned, how do you define it?
Of the young people, or?
Of your data?
So in terms of the variables that I was using, that's already defined. There's a standard way that people are grouped into socioeconomic classes. It's called the NSEC. That's specific to England, I would say. So you would need to, if you're looking at other countries, I think you would need to, look at the specifics of that particular country, because it's not going to work across countries. Yes. So this is, if you go to UK Data Service, you'll find the data there. Okay, I think next one's up. Thank you.